Welcome back, everybody. In this lesson, we are going to be going over, a lot of different properties of functions, how to translate between different representations of functions, and we'll get into some function operations where we're plugging some different kinds of things into functions and seeing how applications play into all of this. In this very specific video, we're going to just be going into the domain and range of a function that's given in its symbolic form. We're going to stick for our purposes today to linear functions and square root functions, some pretty basic ones. As we move through the term and we see different kinds of functions, we'll talk about how to find the domain and range of each specific kind of function individually, while also trying to understand the more general definitions of both domain and range. So let's start with this explanation, this definition of domain and range real quick. We've got the domain of a function is the set of all inputs that produce an output for the function. That is, it's the set of inputs that work in the function or make sense for the function. So it's anything that we can plug in and actually get something out for that specific number. The range of a function is the set of all outputs that the function can produce. It's the set of all values which can be obtained from some given input for the function. So if an output can be reached by the function, then that is part of the range. And then we group all of the possible outputs together, and that the set of all possible outputs together is called the range. So let's take a look at some examples and see how this plays out a bit, at least in some linear scenarios and in some square root scenarios where we'll get something a little bit more interesting. So we want to, for number one, determine the domain and range for the following functions given in symbolic form. So we start with f of x here. That's for part A, f of x equals 7x minus 8. And to determine the domain, we just want to think about the operations. This is taking the input, multiplying it by 7, and then subtracting 8. And we want to say, are there any numbers, like when we're asking the question, what's the domain, we really want to be asking, what numbers can we plug in? And just as importantly, what numbers can we not plug in? So I ask here, is there any number that we cannot multiply by 7 and then subtract 8 from? And if we think about it for a second, the answer is no. We can take any number that we can think of, any real number, fraction, decimal, 0, positive, negative. We can multiply that number by 7 and then subtract 8 from it, and we shouldn't run into any problems. No issues multiplying any number by 7 and then subtracting 8. So that means that the domain is all of the numbers, all real numbers. So I'll say the domain equals the set of all real numbers. I could also put this in interval notation and say that this equals negative infinity to infinity. So this first excuse me. Actually gonna put all of this right here. All right. Let's do the range in, do the domain in red, and then let's do the range stuff in purple. So for the range, we want to think about what numbers can we get out of this function. So if we think about this, this can be a little tricky, and honestly, most of the time for finding range, we're going to look at graphs, especially when functions get a bit more complicated. But if I think about this function, f of x equals 7x minus 8, if I take negative numbers, like really big negative numbers, and multiply them by 7, they'll become really big. So I'm thinking, like, what happens if I multiply a number by 7? Well, if I want a really negative number out, I could plug in a very negative x value. And if I wanted something like 1,000,000 out, then I'd plug in a really big x value so that when I multiplied by 7 and then subtract 8, I could get that as well. We can also think about that this is a line, right? So this is, I mean, like I said, we tend to graph these, but it's a line that looks like this. It keeps going up and down for forever. As we plug in larger and larger x values, the outputs become larger and larger. As we plug in smaller and smaller x values, more and more negative, the outputs become more and more negative. There's no y values that get skipped in any of this. So the range, so no y values get skipped when we plug in all the different x values. So that shows us that we can say that the range is also equal, range is also equal to the set of all real numbers, or the interval from negative infinity to infinity. Let's look at part B. We have g of x equals 12. So for this function, the way this is designed is that for any input, the function g will output 12. And what we note here is that this is true for any input, that I can plug in any x value and the function g will always output 12. So the domain is again all real numbers, the set of all real numbers, or the interval from negative infinity to infinity. I can plug anything in, not a problem, and no matter what, I get out 12. So the domain is the set of all real numbers. The range, well, the only output for this function is the number 12. So the range is just the set with the number 12 in it, nothing else. That's the only possible output for this function. So the range equals the set with just the number 12 in it. And remember, the domain and range are sets, so we do want to use the set notation or an interval notation if that seems to make more sense when describing a domain or a range. So part C, here we have h of x equals the square root of x plus 5. So here's where things are going to start getting a little bit more interesting. I want to say what real numbers, and this is for this class we're sticking to real numbers. If you're familiar with imaginary numbers, complex numbers, we are not worrying about those in any way this term. So just pretend like don't pretend they don't exist. They do exist, but we're not going to use them at all for this class. And so our domain and range is really just going to talk about real numbers. So given a square root, we can only take the square root of positive numbers and 0. Right? So when I look at the inside here of the square root, the inside of the square root, we get that the x plus 5 needs to be greater than or equal to 0, otherwise I wouldn't be able to take its square root. So our restriction for the domain is that the inside of the square root must be positive or 0. So I set up an inequality here, and then we can solve this inequality to get x is greater than or equal to negative 5. And we can then write our domain equals domain equals, we can do set notation, the set of x, such that x is greater than or equal to negative 5. Or we could do interval notation, all the numbers from negative 5 to infinity, including negative 5, always excluding infinity. All right. For the range, I have to think about, okay, the inside of this square root, like if x is negative 5, the inside would be 0. If x equals -5, then we have the square root of 0, which equals 0. So we could get 0 out of this. And as x gets bigger, so that's the left end point from the domain here, when x is -5. So I'm thinking about that, and then I think, okay, as x gets bigger, as it goes to the right, as x can be -5 and -4, the fractions in between there go up to 0, 1, 1.2, 1.9, pi, square roots, any number we can think of. As we plug those in and take the square root of them, we're taking then the square root of bigger and bigger numbers. So as we take the square root of bigger and bigger numbers, the outputs become bigger and bigger. So the smallest output we get for this square root is 0, and then they just keep growing after that. So there's a certain amount of number sense that we get here with how these operations work, right? We take a number, we add 5 to it, and then we take its square root. So if I wanted this, like the output to be something like 100, I would need the square root of 10,000. Square root of 10,000 is 100. If I wanted the output of this function to be, a million, I would need to take the square root of 1 million squared. So we can plug in an x value that's big enough so that we can get a square root that is 1 million. And we can get any output we want to that's bigger than 0 by plugging in a big enough x value. So the range is all the numbers from 0 to infinity. And I'll just do interval notation here. We'll start taking advantage of sometimes it's just easier to write interval notation than set notation. And so we'll just often pick the one that makes the most sense. And that's really the most powerful thing that you want out of the interval notation and the set notation is the ability to do either, so that you have the ability to choose which one makes the most sense. They're both they're both conventional, they're both used throughout mathematics, and so you want to be able to read them when you see them, and you want to be able to write them and be able to choose which one makes the most sense. All right, one more here before we give some for you to try. We have the function k of x equals the negative square root of 6 minus 4x. I'm going to start with that domain again. So we need the inside of the square root. The inside must be greater than or equal to 0. Anytime I have a square root, I cannot take the square root of a negative. So we just have to realize that and then say, okay, I can take the square root of anything bigger than or equal to 0. So we write 6 minus 4x has to be greater than or equal to 0. We'll subtract the 6 from both sides to get negative 4x is greater than or equal to negative 6. And then we need to divide by a negative 4. And this is going to result in flipping the inequality because we've divided by a negative. On the right side, the negatives cancel, and this can reduce to 3 halves. So we get x is less than or equal to 3 halves. So my domain is all the numbers from negative infinity up to positive 3 halves, including positive 3 halves. All right, now we want to look at the range here. So square roots, like if we plug in 3 halves, then k of 3 halves equals negative square root of 6 minus 4 times 3 halves. This equals to the negative square root of 6 minus 4 times 3 halves. The 4 and the 2 reduce to a 2. So show the arithmetic I'm doing here. So cancel the 4 and the 2 to a 1 and a 2. So we get a 6 there. 2 times 3 is 6. And so we get that this equals negative the square root of 0. So that's just 0. So we can get 0 out of this. And then as x becomes smaller and smaller, remember the domain is all the numbers up to 3 halves. So as x gets smaller and smaller. If x is 0, we get the negative square root of 6. If x is negative numbers, then we get a 6 minus 4 times a negative number. Think about that. We get minus 4 times a negative number becomes a positive, and we add 6 to it. So the more negative x gets, the bigger the inside of the square root gets, and so the bigger the output of the square root becomes as well. But because this is negative, we get that the range is all the numbers that are less than or equal to 0, because we're negating all of the square root values. So the square root values can get bigger and bigger and bigger and bigger and bigger, but then we negate them. So we get negate all square root values. And as x gets more and more negative, the square root values become bigger and bigger and bigger, because we're multiplying the negative x values by negative 4 and adding 6. And so we get that when we negate all of these square root values that are getting bigger and bigger and bigger, we get that the range equals negative infinity all the way up to 0, including 0 and nothing else. I'm going to make one other note about these last two problems. A square root function generally looks like this. It looks like it's leveling out, but it does keep growing for forever. So the outputs of this function do keep going up, and we see that the bottom of the graph is at a y value of 0. So that's the minimum there. Oops, I should do that in purple. I'm going to actually do that in black because we're using that for domain and range. For part D, this is a negative square root. So a negative square root is the upside down of that. It goes downward instead of upward in that same kind of shape. And so here we see the biggest y value is 0, and then they keep getting more and more negative. So there's a lot there, and we're not going to expect you to have your head completely wrapped around that, especially the first time you go through this, but give it a shot, and we're going to build on that throughout this term and hopefully give you a better and better understanding of how to come up with domain and range. And we're going to start looking at graphs here in the next, not after, like you're going to do the now you try problems now. Then after you've done those and checked your solutions, then we'll go ahead and go into finding the domain and the range when you're given a graph. I just wanted to start with how, we see something symbolically and we ask, can we find this domain and range? And we definitely can. The range is going to be more difficult. And so when we move on to the next video and or the next topic and look at domain and range with a graph, some of this might make a little bit more sense. So we'll just keep adding to our understanding. All right, thank you very much for watching. Give the Now You Try problems that you find in Mindomo a shot, and then watch the next video to check your answers on that. We'll go from there.